Close your eyes for a moment. Now open them. The light that just hit your eyes? It was bent, curved, twisted by invisible forces before it reached you. And here's what's going to keep you awake tonight. Every single thing you've ever seen with your eyes has been a lie. Not because the universe is trying to deceive you, but because gravity has been secretly editing reality before it reaches your retinas. Right now, at this very moment, you're looking at stars that died millions of years ago. You're seeing galaxies that don't exist in those positions anymore. And the craziest part? Some of the light reaching your eyes has been so dramatically warped by gravity that you're seeing the same object in multiple places at once. The universe is showing you cosmic miracles, and you've been scrolling past them your entire life. What if I told you that gravity doesn't just pull things down? What if I told you that gravity is literally bending the fabric of space itself, and light is just following the curves like a car on a roller coaster? What if everything you learned about gravity being a force was fundamentally wrong? By the end of this journey, you're going to understand something that less than 1% of humanity truly grasps. You're going to see the universe the way Einstein saw it. And I promise you, you'll never look at the night sky the same way again. But before we dive into this mind-bending journey, do me a favor. Hit that like button right now, because what you're about to learn took humanity thousands of years to figure out, and I'm about to give it to you in the next few hours. Subscribe and turn on notifications, because this is part of a series that's going to fundamentally change how you understand reality. And drop a comment telling me, what country are you watching from? And what time is it where you are? I want to know how many of us are having our minds blown simultaneously across this planet. Let's start with something you think you understand. Gravity. You drop a ball, it falls down. Simple, right? Wrong. That ball isn't falling. And down doesn't exist. In 1687, Isaac Newton published his Principia Mathematica and told us that gravity was a force, an invisible hand reaching across space, pulling objects together. For over 200 years, this worked perfectly. We calculated planetary orbits, we understood tides, we sent astronauts to the moon using Newton's equations. But Newton himself knew something was wrong. He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Newton was bothered by the same thing that should bother you. How does the Earth know the moon is there? How does gravity travel through empty space? What is it made of? For 2 centuries, nobody had an answer. Then in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that broke physics. He proved that space and time weren't separate things. They were woven together into a single fabric he called spacetime. And here's where your brain needs to shift gears. Spacetime isn't just where things happen. Spacetime is a thing. A physical thing that can be bent, stretched, and twisted. Think of it like this. Imagine the universe as a giant trampoline. Now place a bowling ball in the center. The trampoline dips, curves, bends around that heavy object. If you roll a marble across this trampoline, it won't travel in a straight line. It'll curve around the bowling ball, following the depression in the fabric. The marble isn't being pulled by the bowling ball. The marble is simply following the straightest possible path through curved space. This is gravity. Mass doesn't pull on other mass. Mass curves spacetime, and objects follow those curves. You're not being pulled down toward the Earth right now. You're sitting still in spacetime, and the Earth is accelerating upward into you. Yes, you read that right. The ground beneath your feet is constantly accelerating upward at 9.8 meters per second squared, pushing into you. And only the rigidity of the Earth's surface stops you from following your natural path through curved spacetime. Einstein published this complete theory, general relativity, in 1915. and he made a prediction that seemed impossible. If mass curves spacetime and light travels through spacetime, then gravity must bend light. Here's your first mind-blown moment. Light always travels in straight lines, always, without exception. But those straight lines exist in curved space, which means from our perspective, light curves. In 1919, a British astronomer named Arthur Eddington set out to test Einstein's wild prediction. During a solar eclipse, he photographed stars near the sun's edge. According to Newton, the sun's gravity should have zero effect on starlight because light has no mass. But according to Einstein, the sun's massive bulk should curve spacetime so severely that starlight passing nearby should bend. When Eddington developed those photographs, he saw stars in positions they shouldn't be. The sun had bent their light, displacing their apparent positions by exactly the amount Einstein predicted, 1.75 arcseconds. That's less than the width of a human hair seen from 50 feet away. But it was enough to prove that Newton was wrong and Einstein was right. Space itself was curved, and light was just following the geometry. This discovery made Einstein an overnight celebrity. But here's what will blow your mind. That same bending of light is happening right now, all around you, constantly. Every massive object in the universe is bending the light that passes near it. Black holes bend light so severely that nothing can escape. Galaxies bend light from objects behind them. Even your body bends light, though by an amount so tiny that no instrument could ever measure it. Now let's go deeper. If gravity bends light, and light is how we see things, then what we see is not what actually is. We're not seeing the universe as it is. We're seeing a distorted funhouse mirror version of reality, warped by every massive object between us and whatever we're looking at. Astronomers call this gravitational lensing, and it's given us some of the most spectacular discoveries in modern astronomy. In 1979, astronomers Dennis Walsh, Bob Carswell, and Ray Wayman discovered something impossible, a quasar, one of the brightest objects in the universe that appeared to exist in two places at once. They were seeing the same object, but its light had taken two different paths around a massive galaxy between us and the quasar. Gravity had literally created a cosmic double image. But gravitational lensing does something even more spectacular. Sometimes, when the alignment is perfect, when a massive galaxy sits directly between us and a distant object, the background object's light is bent around the galaxy from all directions. Instead of seeing multiple images, we see a ring. A perfect circle of light called an Einstein ring, where a distant galaxy has been smeared into a halo around a closer galaxy. Think of it like this. You're trying to see a streetlight behind a giant glass ball. The ball bends the light from all directions, and instead of seeing one point of light, you see a ring. Except the glass ball is a galaxy containing hundreds of billions of stars, and the streetlight is another galaxy billions of light years away. These Einstein rings aren't just beautiful, they're tools. By measuring how much the light has been bent, astronomers can calculate the mass of the lensing galaxy with incredible precision. And here's where things get weird. When they do these calculations, the math doesn't work. The visible matter in these galaxies, all the stars and gas we can see, isn't massive enough to bend light the way we observe. Something invisible, something that doesn't emit or absorb light, is providing most of the gravitational pull. We call it dark matter, and it makes up 85% of the matter in the universe. We can't see it. We don't know what it's made of, but we know it's there because gravity bends light, and the light has been bent by something we can't see. Let's talk about light itself, because what you're about to learn is going to rewire how you think about time, space, and causality. Light travels at 299,792,458 meters per second in a vacuum. We usually round this to 300,000 kilometers per second, or about 186,000 miles per second. This isn't just fast. This is the speed limit of the universe. Nothing can travel faster. Not spaceships, not particles, not information, not anything. This speed limit is woven into the very fabric of reality. But why? Why does light travel at exactly this speed, and why can't anything go faster? Here's where your brain might break a little. Light always travels at the same speed for everyone, no matter how fast they're moving. If you're standing still and measure the speed of a passing light beam, you get 300,000 kilometers per second. If you're in a spaceship traveling at 99% the speed of light and measure that same beam passing you, you still get 300,000 kilometers per second. This is impossible according to common sense, but it's absolutely true according to reality. Think of it like this. Imagine you're on a train traveling at 100 kilometers per hour. You throw a ball forward at 10 kilometers per hour relative to you. Someone standing outside the train sees that ball moving at 110 kilometers per hour. Velocities add up. Except with light, they don't. If that train is traveling at 99% the speed of light and you shine a flashlight forward, that light doesn't travel at 99% plus 100% the speed of light. It travels at exactly 100% the speed of light. No more, no less. How is this possible? Einstein figured it out. If the speed of light is constant for everyone, then something else has to give. That something is time and space themselves. Time slows down for moving objects. Space contracts for moving objects. If you're moving fast enough, your seconds become longer and your meters become shorter, compensating perfectly so that light always travels at the same speed for you. This isn't a trick or an illusion. This is how reality actually works. Time is not a universal constant ticking away uniformly everywhere. Time is relative, flexible, malleable. And gravity makes it even weirder. Here's your second mind-blown moment. Gravity doesn't just bend space, it bends time. The stronger the gravity, the slower time flows. If you're standing on the surface of a planet, time is moving slower for you than for someone orbiting above you. If you're near a black hole, time nearly stops compared to someone far away. This has been measured. In 1971, physicists Joseph Hafele and Richard Keating took atomic clocks onto commercial airplanes and flew them around the world. When they compared those clocks to identical clocks that stayed on the ground, the flying clocks had gained about 200 nanoseconds. Not much, but exactly what Einstein's equations predicted. The clocks at higher altitude, experiencing slightly less gravity, ran slightly faster. Your head right now is aging faster than your feet. The difference is minuscule, about 90 nanoseconds over 80 years, but it's real. Gravity at your feet is slightly stronger than at your head, so time flows slightly slower down there. You are not experiencing a single, uniform flow of time through your body. Different parts of you are experiencing time at different rates. GPS satellites have to account for this. They're orbiting at about 20,000 kilometers altitude, where gravity is weaker, and they're moving at about 14,000 kilometers per hour. Both effects influence how fast their onboard clocks tick compared to clocks on Earth's surface. If GPS didn't correct for relativistic time dilation, your navigation would be off by several kilometers within a single day. Now let's connect this back to light. Light doesn't just travel through space, it travels through time. We call its path through four-dimensional spacetime a light cone. Everything in your past exists inside your past light cone, the set of all events that could have sent light to reach you right now. Everything in your future exists inside your future light cone, the set of all events you could possibly influence by sending light from this moment. And here's the truly profound realization. Nothing outside your light cone can affect you, and you cannot affect anything outside your light cone. The speed of light creates a boundary around your existence, defining what parts of the universe you can interact with, and what parts are forever beyond your reach. Now we're ready to talk about the most extreme demonstration of gravity and light interacting: black holes. These aren't just really dense things. Black holes are regions where space-time has been curved so severely that it tears, where the geometry becomes infinite, where the rules break down. In 1916, just months after Einstein published general relativity, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I. Despite the chaos of war, he solved Einstein's equations for a perfectly spherical mass and discovered something terrifying. If you compress enough mass into a small enough space, space-time curves so extremely that nothing, not even light, can escape beyond a certain radius. This radius, now called the Schwarzschild radius, defines the event horizon of a black hole. For Earth to become a black hole, you'd have to crush it down to about 9 millimeters in diameter. For the Sun, about 3 kilometers. For you, assuming you weigh around 70 kilograms, your Schwarzschild radius would be about 10 to 25 meters, far smaller than a proton. The event horizon isn't a physical surface. It's a boundary in space-time itself. Cross it, and your future becomes the singularity. Not metaphorically, literally. Inside the event horizon, the direction toward the singularity becomes timeward. You can no more avoid hitting the singularity than you can avoid moving forward in time. The singularity isn't a place you go to. It's a moment in time you will reach, inevitably, like tomorrow. Here's your third mind-blown moment. From the perspective of someone falling into a black hole, they cross the event horizon and hit the singularity in finite time. Maybe seconds, maybe hours, depending on the black hole's size. But from the perspective of someone watching from a safe distance, the falling person never crosses the event horizon. Ever. They appear to slow down as they approach, getting dimmer and redder, asymptotically approaching the horizon, but never quite reaching it. The falling person's clock has slowed down so much relative to the outside universe that infinite outside time passes while finite time passes for them. Both perspectives are equally valid. This isn't a contradiction. This is what reality looks like when gravity becomes extreme. Light near a black hole does something extraordinary. At exactly 1.5 times the Schwarzschild radius, light can orbit the black hole. Photons circle endlessly, trapped in what's called the photon sphere. If you were hovering at this distance and looked sideways, you'd see the back of your own head, illuminated by light that had traveled all the way around the black hole. Below the photon sphere, but above the event horizon, light can still escape, but only if aimed nearly straight up. Point your flashlight at even a slight angle from vertical, and the light curves back down, trapped by the overwhelming curvature of spacetime. This region is called the ergosphere, and it's where things get really weird. In 1969, physicist Roger Penrose proved that you could extract energy from a rotating black hole through a process now called the Penrose process. Drop something into the ergosphere, have it split into two pieces with one piece falling in and the other escaping, and the escaping piece can leave with more energy than you started with. You've extracted rotational energy from the black hole itself. An advanced civilization could, in principle, dump their garbage into a black hole and use the Penrose process to power their entire civilization. The universe's ultimate recycling program. But black holes don't just trap light. They also create it. In 1974, Stephen Hawking proved that black holes aren't completely black. Quantum mechanics allows particle pairs to spontaneously form near the event horizon. Normally, these particles would immediately annihilate. But if one falls into the black hole while the other escapes, the escaping particle becomes real radiation. The black hole loses mass in the process. Over unimaginable timescales, black holes evaporate. A solar mass black hole would take about 1,067 years to evaporate via Hawking radiation. The universe is only 13.8 billion years old. But given enough time, every black hole in the universe will evaporate into nothing but faint radiation. leaving no trace they ever existed. Remember gravitational lensing? We're about to discover how it's revolutionizing astronomy and revealing universes beyond what should be visible. The most powerful gravitational lenses in the universe aren't individual galaxies. They're galaxy clusters, massive collections of hundreds of thousands of galaxies bound together by gravity, floating in even more massive halos of dark matter. These cosmic behemoths can bend light so dramatically that they act like natural telescopes, magnifying distant objects by factors of 10, 50, or even 100. In 2012, using a galaxy cluster called MAX J0647, astronomers detected a galaxy that existed when the universe was only 420 million years old. This galaxy is so distant and faint that even the Hubble Space Telescope couldn't have seen it directly. But the galaxy cluster's gravity magnified its light, making the invisible visible. Think of it like this. You're trying to read microscopic text, normally impossible. But place a magnifying glass over it, and suddenly the letters become clear. Galaxy clusters are nature's magnifying glasses, bending spacetime itself to bring the early universe into focus. These gravitational telescopes have revealed something extraordinary. The universe has been making galaxies far earlier and faster than we thought possible. We're seeing fully formed galaxies less than 500 million years after the Big Bang. That's like finding a modern city in an archaeological dig that should only contain primitive tools. The universe figured out how to make complex structures far faster than our models predicted. But gravitational lensing does something even more spectacular. Sometimes the alignment is so perfect that background galaxies get stretched and distorted into long arcs, painted across the sky like cosmic brushstrokes. The Hubble Space Telescope has captured images of single galaxies that appear multiple times in the same photograph, their light taking different paths around a massive cluster, creating a cosmic hall of mirrors. One particular cluster, called Abell 2744, has been nicknamed Pandora's cluster. When you look at deep images of this cluster, you see hundreds of distorted arcs. Each arc is a distant galaxy, its light bent and amplified by the cluster's enormous mass. Some of these background galaxies appear multiple times in the same image. You're seeing the same object from different angles simultaneously, its light having taken different paths through curved spacetime. Here's where things get profound. By carefully mapping all these arcs, measuring their distortions, and calculating how much gravity was needed to bend them, astronomers can create mass maps of galaxy clusters. They can literally weigh the universe, accounting for every gram of matter, visible or invisible. And when they do this, they keep finding the same thing. Most of the universe is missing. For every kilogram of normal matter, stars and gas and planets in you, there are about 5 kilograms of dark matter. Something invisible, something that doesn't interact with light at all except through gravity, is providing most of the gravitational pull holding galaxy clusters together. We know it's there because of what it does to light. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light, but it does bend light because it has mass, and mass curves spacetime. We're mapping the invisible through its shadow, seeing dark matter only by the way it distorts images of bright objects behind it. In 2006, astronomers observed 2 galaxy clusters colliding. It's called the Bullet Cluster. When they mapped where the visible matter ended up versus where the gravitational lensing showed the mass to be, they found something extraordinary. The hot gas from both clusters had collided and stopped in the middle, but the dark matter had passed right through, like 2 ghosts passing through each other. The mass had separated from the light-emitting matter. This was the first direct proof that dark matter was real and distinct from normal matter. We've talked about how gravity bends space and how it slows time. Now let's talk about how gravity can shake space-time itself. Einstein predicted in 1916 that violent events, like colliding black holes or exploding stars, should create ripples in space-time itself. These gravitational waves would spread outward at the speed of light, stretching and squeezing space as they pass. But Einstein thought they'd be far too weak to ever detect. He was almost right. For 100 years, no one could measure a gravitational wave. The distortions they create are infinitesimally small. When a gravitational wave passes through you, it stretches you in one direction while compressing you in the perpendicular direction. But by how much? A gravitational wave from colliding black holes billions of light years away would change your height by less than the width of an atomic nucleus. Your entire body stretched and squeezed, but by an amount smaller than the smallest atom. In 1972, physicists Rainer Weiss, Kip Thorne, and Ronald Drever began designing an instrument sensitive enough to detect this impossible signal. They proposed using lasers and mirrors to measure the tiny distance changes caused by passing gravitational waves. The instrument would need to measure changes of 10 to 18 meters. That's 1,000th the width of a proton. It took 40 years and over $1 billion to build. The Laser Interferometer Gravitational Wave Observatory, LIGO, two massive L-shaped detectors, one in Louisiana and one in Washington state, each with 4-kilometer-long arms, where laser beams bounce back and forth between mirrors. If a gravitational wave passes through, one arm stretches while the other compresses, changing the distance the light travels by an almost undetectable amount. On September 14, 2015, at 5:51 a.m. Eastern Time, both LIGO detectors registered a signal, a chirp lasting a fifth of a second, rising in frequency and amplitude before cutting off. The two black holes, each about 30 times the sun's mass, had been spiraling together for millions of years. In their final seconds, they orbited each other hundreds of times per second, moving at half the speed of light, before finally merging into a single black hole. The collision was so violent, it released more energy in that fifth of a second than all the stars in the observable universe combined. 3 solar masses worth of matter, about the mass of 600,000 Earths, was converted into pure gravitational wave energy according to E.E. Cole's MC. That energy rippled out through space, stretching and squeezing everything in its path, until 1.3 billion years later, it passed through Earth, wiggling LIGO's mirrors by less than the width of a proton. This was your fourth mind-blown moment. On that September morning, humans detected the collision of 2 black holes more than 1 billion light years away by measuring the vibration of spacetime itself. We didn't see light from this event. We couldn't. Black holes don't emit light. We heard the spacetime ring like a bell as 2 of the universe's most extreme objects became one. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Black hole collisions, neutron star collisions, asymmetric supernova. We're listening to the universe in an entirely new way, detecting events that are completely invisible to light-based telescopes. But here's the connection that brings everything together. In August 2017, LIGO detected gravitational waves from 2 colliding neutron stars. At the exact same time, telescopes around the world detected a gamma-ray burst from the same location. For the first time in human history, we detected the same cosmic event using both gravitational waves and light. This is the future of astronomy. Multi-messenger observations, where we watch the universe with both light and gravity simultaneously, getting a complete picture of the most violent events in the cosmos. Gravity and light, the 2 messengers that carry information across the universe, observe together, telling us a more complete story than either could tell alone. Now we need to talk about something even stranger. The universe is expanding, and this expansion is making parts of the universe disappear forever. In 1929, Edwin Hubble made a discovery that changed everything. He measured the light from distant galaxies and found something shocking. Nearly all of them were redshifted, meaning their light had been stretched to longer, redder wavelengths. The further away the galaxy, the more its light was redshifted. The only explanation: space itself was expanding, stretching the light as it traveled through that expanding space. Think of it like this. Draw dots on a balloon representing galaxies. Now inflate the balloon. All the dots move away from each other, not because they're traveling through the balloon's surface, but because the surface itself is expanding. Space works the same way. Galaxies aren't flying through space away from each other. Space is growing, carrying the galaxies apart. But here's where light and gravity create something profound and disturbing. The universe is about 13.8 billion years old. Light has had 13.8 billion years to travel. You might think this means we can see objects up to 13.8 billion light years away. But you'd be wrong. Because space has been expanding while that light was traveling, we can actually see objects that are now about 46 billion light years away. The observable universe, the sphere of all things we could possibly see, has a radius of 46 billion light years. But here's the disturbing part. There's more universe beyond that boundary. Much more, possibly infinitely more. But we will never see it, can never see it, because the space between us and those distant regions is expanding faster than light can cross it. Those photons are like someone running up a down escalator that's moving faster than they can run. They make progress, but they never reach the top. And it gets worse. In 1998, two teams of astronomers studying distant supernova made a discovery that won them the Nobel Prize. The expansion of the universe is accelerating. Something is pushing space apart, faster and faster over time. We call it dark energy, and it makes up 68% of the universe. We don't know what it is. We don't know where it comes from. But its effect is undeniable. The universe's expansion is speeding up. This means galaxies beyond a certain distance are receding from us faster than light. Not traveling through space faster than light, which is impossible, but being carried away by expanding space itself. Their light is still heading toward us, but the space between us is growing faster than the light can cross it. Like that person on the down escalator, running but never getting closer. Here's your fifth mind-blown moment. There are galaxies we can see right now that we will never be able to reach, even if we left today traveling at the speed of light. We're looking at parts of the universe that are already beyond our cosmic event horizon. We're seeing their ancient past, but their present and future are forever disconnected from us. And over billions of years, more and more galaxies will cross this horizon and disappear from view as space carries them beyond the point of no return. In about 100 billion years, all the galaxies outside our local group will have receded beyond the cosmic horizon. Some future astronomer, looking up at the night sky from Earth or whatever planet remains, will see a handful of nearby galaxies and nothing else. The rest of the universe will have expanded away, their light redshifted into undetectability. That astronomer will have no evidence that the universe is expanding at all. They'll look at a seemingly static universe and have no way to discover the Big Bang, no way to know that space had a beginning, no way to understand that they're living in a vast expanding cosmos. We live in a special time, cosmically speaking. A time when the universe has expanded enough to be interesting, but not so much that all evidence of the expansion has disappeared. We can see our cosmic history written in the light from distant galaxies. Future civilizations won't have that privilege. Let's go back to the beginning. Not to the Big Bang itself, but to the moment when the universe first became transparent to light. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Protons and electrons existed, but couldn't form atoms because it was too hot. And in this plasma state, light couldn't travel. Photons would be emitted, travel a tiny distance, and be absorbed by a charged particle. The universe was opaque, like being inside a thick fog. But as the universe expanded, it cooled. When the temperature dropped to about 3,000 degrees Kelvin, something magical happened. Protons and electrons combine to form neutral hydrogen atoms. This process is called recombination. And suddenly, with no more free electrons to scatter off of, photons could travel freely. The universe became transparent. The light emitted at that moment has been traveling through space ever since. But remember, space has been expanding. That light, originally emitted at visible wavelengths as red light, has been stretched by the universe's expansion. Its wavelength is increased by a factor of about 1,000. Red light has become microwave radiation. This is the cosmic microwave background, or CMB. It's the oldest light in the universe, a snapshot of what the cosmos looked like when it was 380,000 years old. And it's everywhere. Right now, from every direction in space, ancient photons from the beginning of time are washing over you. About 400 of them pass through your thumb every second. In 1964, Arno Penzias and Robert Wilson were testing a microwave antenna and kept detecting annoying background noise. They cleaned out pigeon droppings, checked all their equipment, but the noise remained, coming equally from all directions, unchanging in intensity. They'd accidentally discovered the CMB, the echo of the Big Bang itself. But here's what makes the CMB profound. It's not perfectly uniform. In 1992, the COBE satellite made detailed measurements and found tiny variations, about 1 part in 100,000, in the temperature of the CMB across the sky. These variations are the seeds of all structure in the universe. Slightly denser regions where gravity pulled in more matter, eventually forming galaxies, stars, planets, and you. The pattern of these variations tells us the geometry of the universe. By measuring their size and distribution, we can calculate whether space is flat, curved like a sphere, or curved like a saddle. The answer: flat to within measurement error. If you travel in a straight line through space, you'll never curve back to your starting point. Space extends, as far as we can tell, infinitely. These same measurements tell us the age of the universe: 13.8 billion years. The composition of the universe: 68% dark energy, 27% dark matter, 5% normal matter. The rate of expansion. Everything we know about the universe's history, geometry, and contents comes from careful measurements of light that's been traveling for 13.8 billion years. But here's something that should make you pause. When we look at the CMB, we're looking at the surface of a sphere surrounding us, centered on our location, 46 billion light years in radius. We're at the center of our observable universe. But that doesn't mean we're special. Every observer, anywhere in the universe, is at the center of their own observable universe, looking out at their own CMB sphere. This is the cosmic horizon. It's not an edge where the universe ends. It's a limit on what we can see, defined by the finite age of the universe and the finite speed of light. Beyond our horizon, the universe continues, possibly infinitely. Other observers out there have their own horizons. Some of their observable universe overlaps with ours. Some doesn't. There are regions of space that we can see but they cannot, and regions they can see but we cannot. Gravity and light together define what portions of the infinite universe are accessible to us, creating boundaries not in space itself, but in what we can possibly know. Everything we've discussed leads to something extraordinary. The speed of light and the curvature of space-time create actual, literal time travel. Not science fiction, reality. Every time you look at something, you're seeing its past. Look at your hand. You're seeing it as it was a few nanoseconds ago. The time light took to travel from your hand to your eyes. Look at the moon. You're seeing it as it was 1.3 seconds ago. Look at the sun, 8 minutes ago. Look at the nearest star system, Alpha Centauri, 4.4 years ago. Look at the Andromeda Galaxy, 2.5 million years ago. Look at the most distant galaxies visible to the Hubble Space Telescope, over 13 billion years ago, when the universe was young and nothing like it is today. You are literally, physically, looking back in time. The telescope is a time machine. The universe has helpfully preserved its history for us in the form of light that's been traveling for billions of years. We can see cosmic evolution, watching galaxies form and change by looking at objects at different distances and therefore different times. But gravity makes this weirder. Remember, time slows down in strong gravity. If you could hover just above a black hole's event horizon for a while, then fly back to Earth, you'd discover that far more time had passed here than for you. From your perspective, maybe a year passed. From Earth's perspective, maybe decades or centuries. You've traveled to Earth's future. This isn't theoretical. 2 atomic clocks, synchronized on Earth, and one taken on a high-speed flight around the world, will be out of sync when reunited. The traveling clock will have experienced less time. It will be younger. This has been measured repeatedly and is now used routinely in GPS satellites. Here's your 6th mind-blown moment. The GPS satellite flying overhead right now is experiencing time faster than you are because it's in weaker gravity and moving at high speed. Engineers have to account for this. The satellite's clock is intentionally slowed before launch so that once in orbit, relativistic effects will speed it up to match ground time. Without correcting for general and special relativity, GPS would accumulate position errors of several kilometers per day. The technology in your pocket depends on understanding how gravity and motion affect the flow of time. Every time you use GPS navigation, you're using Einstein's equations, accounting for time dilation caused by gravity and velocity. Your phone is doing relativistic physics calculations constantly, proving that time travel isn't science fiction, it's engineering. But there's a catch. You can travel to the future. That's easy. Just move fast or hang out in strong gravity. But traveling to the past seems impossible. If you could travel backward in time, you could create paradoxes. Kill your grandfather before your father was born, which means you were never born, which means you couldn't have traveled back to kill your grandfather. The universe doesn't seem to allow this. Or does it? In 1949, mathematician Kurt Gödel found an exact solution to Einstein's equations that allowed closed time-like, curved paths through spacetime that loop back on themselves. Travel along one of these paths and you'd arrive back at your starting point in space and time before you left. True time travel to the past. The catch. Gödel's solution required the universe to be rotating, and our universe isn't rotating. But since then, physicists have found other solutions that allow closed time-like curves, rotating black holes, infinite rotating cylinders, wormholes. Each requires conditions that may not exist in nature, but they're allowed by the mathematics of general relativity. The universe seems to be telling us something profound. Time travel to the past isn't forbidden by the laws of physics, but it might be forbidden by the initial conditions of the universe or by quantum mechanics. We're still figuring out which. If gravity can bend space and time, could it bend them so severely that distant points in the universe connect? Could you step through a doorway in New York and emerge in the Andromeda Galaxy? The mathematics says yes. These connections are called wormholes, officially known as Einstein-Rosen bridges. In 1935, Einstein and physicist Nathan Rosen discovered that the equations of general relativity naturally produced these tunnel-like connections between different regions of spacetime. Think of it like this. Imagine space as a flat sheet of paper. 2 points might be far apart if you measure distance along the paper's surface. But if you fold the paper so those points touch, you could poke a hole through both layers. Now there's a shortcut connecting them. That's a wormhole, a tunnel through higher dimensional space connecting distant locations. But here's the problem. Wormholes, as they naturally appear in Einstein's equations, are catastrophically unstable. They collapse almost instantly, pinching off faster than light could travel through them. For a wormhole to remain open long enough for anything to pass through, you'd need exotic matter with negative energy density. Negative energy sounds like science fiction, but quantum mechanics actually allows it. The Casimir effect, discovered in 1948, shows that if you place two metal plates extremely close together in a vacuum, quantum fluctuations create a region between the plates with less energy than the surrounding vacuum. The plates experience a tiny attractive force. The space between them has negative energy density. The problem is scale. To hold open a wormhole wide enough for a person, you'd need negative energy in macroscopic amounts. We can create negative energy in microscopic quantities for microseconds. Scaling that up might require technology we won't have for centuries, if ever. But if you could create a traversable wormhole, something fascinating happens. Remember that gravity affects time? If you take one end of a wormhole on a high-speed journey while leaving the other end stationary, the traveling end will age slower. Now you have two wormhole mouths that exist at different times. Step through one end, and you don't just travel through space, you travel through time. Physicist Kip Thorne worked out these equations in the 1980s. While consulting on Carl Sagan's novel, Contact, Sagan asked whether wormholes could be scientifically plausible. Thorne's analysis showed they could be, with the right conditions. The novel's wormhole became one of the first scientifically grounded depictions of these objects in popular fiction. But here's where things get philosophically weird. If wormholes allow time travel, and time travel creates paradoxes, maybe the universe protects itself. Physicist Stephen Hawking proposed the chronology protection conjecture. The laws of physics conspire to prevent time travel to the past, perhaps by causing wormholes to collapse exactly when they're about to create a time machine, perhaps through quantum effects we don't yet understand. We're touching the edge of known physics here. General relativity says wormholes can exist. Quantum mechanics might say they can't remain stable. We need a theory of quantum gravity to know for sure, and we don't have one yet. This is one of the great unsolved problems in physics. How do gravity and quantum mechanics work together when spacetime itself becomes quantum? Speaking of quantum mechanics, let's talk about one of the deepest puzzles in physics. What happens to information that falls into a black hole? Here's the setup. In quantum mechanics, information is never destroyed. If you know the complete state of a system at one time, you can in principle calculate its state at any other time, forward or backward. This is called unitarity. It's a fundamental principle, but black holes seem to violate this. If you throw a book into a black hole, all the information in that book, every letter, every word, every pattern of ink on paper disappears from the universe. It's behind the event horizon, causally disconnected from everything outside. And according to Hawking's calculations, when the black hole eventually evaporates via Hawking radiation, that radiation is completely random, containing no information about what fell in. Information destroyed. Unitarity violated. Fundamental principles broken. This is the black hole information paradox, and it's been driving physicists crazy since. Hawking discovered it in 1974. Stephen Hawking himself initially believed information was truly destroyed, that black holes were exceptions to quantum mechanics. This sparked one of the longest debates in theoretical physics. In 1997, Hawking made a bet with fellow physicists Kip Thorne and John Preskill. The bet? Whether information is destroyed in black holes. Hawking and Thorne bet it was destroyed. Preskill bet it was preserved somehow. In 2004, Hawking conceded the bet. New calculations suggested that quantum effects at the event horizon might encode information about what fell in, and this information might gradually leak out through subtle correlations in the Hawking radiation. The information isn't destroyed. It's scrambled and encoded in ways we don't yet fully understand. But here's what makes this profound. This debate isn't just about black holes. It's about the fundamental nature of reality. Can information be destroyed? Are quantum mechanics and gravity compatible? Is space-time truly continuous, or does it become grainy and discrete at tiny scales? These questions connect to something even deeper, the holographic principle. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind proposed something radical. They suggested that all the information inside a volume of space could be encoded on its boundary, like a hologram. A three-dimensional region could be completely described by two-dimensional information on its surface. Black holes support this idea. The entropy of a black hole, a measure of its information content, is proportional to the surface area of its event horizon, not its volume. A bigger event horizon surface means more entropy, as if the information is stored on the horizon itself, rather than in the volume inside. If this principle applies to black holes, maybe it applies everywhere. Maybe the entire three-dimensional universe we perceive is actually information encoded on a two-dimensional surface at the edge of the cosmos. Maybe space itself is an illusion, an emergent property arising from quantum information stored on a distant boundary. This sounds like mysticism, but it's serious physics with mathematical backing. Several approaches to quantum gravity, including string theory, suggest the holographic principle is correct. The universe might literally be a hologram. And here's how this connects to light and gravity. Light carries information. Gravity affects how that information propagates. The interplay between them defines what information can be accessed, what can be known, what can persist versus what must be forgotten. Every photon reaching your eye carries bits of information about its source. Every gravitational interaction encodes information about mass and energy. The universe is fundamentally about information flow, and gravity and light are the messengers. Now we need to talk about what empty space actually is, because it turns out emptiness is incredibly busy. In quantum field theory, the vacuum isn't empty. It's seething with virtual particles. Particle-antiparticle pairs that spontaneously appear, exist for a fleeting moment, then annihilate. An electron and positron pop into existence, live for a time determined by Heisenberg's uncertainty principle, then disappear. This happens everywhere, constantly, throughout all of space. You might think this is just mathematical abstraction, but virtual particles have measurable effects. The Casimir effect, which we mentioned earlier, is caused by virtual particles. There are slightly fewer virtual particle pairs between two metal plates than in the surrounding vacuum, because only certain wavelengths fit in the gap. This creates a pressure imbalance that pushes the plates together. The Lamb shift in hydrogen spectrum is caused by virtual particles. The electron in a hydrogen atom is constantly interacting with virtual particles in the vacuum, slightly changing its energy levels. We've measured this to extraordinary precision. Virtual particles are as real as anything in physics. Now add gravity to this picture. Virtual particles have energy, and energy has mass via E equals mc, and mass creates gravity. The quantum vacuum should gravitate. But when physicists calculate how much, they get an answer that's wrong by a factor of 10,120. That's 1 followed by 120 zeros. The worst prediction in the history of science. This is the cosmological constant problem. The vacuum should have enormous energy density and should create enormous gravity, either collapsing the universe instantly or expanding it so fast nothing could form. But it doesn't. The vacuum's actual energy density is about 10,120 times smaller than predicted. Why? Nobody knows. This is one of the deepest mysteries in physics. Something is canceling out the vacuum energy, reducing it to the tiny value we observe. But we don't know what or how. That tiny value, by the way, is dark energy. The mysterious force accelerating the universe's expansion is likely the energy of the quantum vacuum itself. Empty space has weight, and that weight is pushing the universe apart, faster and faster. Here's your seventh mind-blown moment. Dark energy, the dominant component of the universe's mass energy, might be the quantum uncertainty of empty space itself. The vacuum fluctuations that create virtual particles also create a subtle pressure that's tearing the universe apart. The frenetic activity of empty space might be the force that determines the universe's ultimate fate. And light interacts with this quantum vacuum. When photons travel through space, they're constantly interacting with virtual particle pairs. In strong electromagnetic fields, photons can even split into real electron-positron pairs. In the intense gravity near black holes, the vacuum's quantum fluctuations become real Hawking radiation. The line between real and virtual becomes fuzzy. Gravity also affects the quantum vacuum. Strong gravitational fields change which vacuum states are possible, altering the spectrum of virtual particles. Near a black hole's event horizon, the vacuum is different from the vacuum in flat space. Gravity and quantum mechanics are dancing together in ways we're only beginning to understand. Some physicists think this dance holds the key to quantum gravity. Maybe space and time themselves emerge from quantum entanglement. Maybe gravity isn't a fundamental force, but an entropic phenomenon arising from quantum information. These ideas are speculative, but mathematically serious. We might be on the verge of understanding that space-time itself is quantum, that the smooth geometric picture Einstein gave us is an approximation that breaks down at tiny scales. At the Planck scale, about 10 to 35 meters in y-43 seconds, quantum fluctuations in space-time itself become important. Space and time might become foamy, discontinuous, discrete. Light propagating at these scales might not travel smoothly, but hop from point to point. Gravity at these scales might not curve space continuously, but warp it in quantum jumps. We can't probe these scales experimentally yet. The energies required exceed anything our particle accelerators can produce by factors of trillions. But the mathematics of quantum field theory in curved spacetime gives us hints. And those hints suggest that the very fabric of reality is far stranger than either Einstein's smooth spacetime or the quantum fields we know from particle physics. The early universe was hot, unimaginably hot. In the first fraction of a second after the Big Bang, temperatures exceeded trillions of degrees. Under these conditions, physics was very different. As the universe expanded and cooled, it went through phase transitions, similar to water freezing into ice. And just like ice forming on a pond creates cracks and imperfections, phase transitions in the early universe might have created defects in the fabric of spacetime itself. One possibility: cosmic strings. These are one-dimensional defects, infinitely thin but potentially stretching across the universe. They're not made of matter. They're topological defects in quantum fields, places where the field couldn't decide which value to take as it cooled and got stuck in a higher energy state. Cosmic strings are predicted to have enormous mass. A cosmic string 1 kilometer long might weigh as much as the Earth. And this enormous mass, concentrated in one dimension, creates wild gravitational effects. A cosmic string doesn't attract objects toward it like a normal massive object. Instead, it creates a conical deficit in spacetime. Imagine cutting a wedge out of a flat sheet and gluing the edges back together. The sheet is now cone-shaped with a deficit angle. That's what a cosmic string does to space. As you circle around it, you don't travel the full 360 degrees you'd expect. You might only travel 350 degrees or 340 degrees. Light passing near a cosmic string follows this geometry, bending in unusual ways. If a cosmic string passed between us and a distant galaxy, we'd see a double image of that galaxy. But unlike gravitational lensing from a massive object, the two images would be identical: same brightness, same size, same everything, just offset in position by the deficit angle. We haven't found cosmic strings yet, but we're looking. Their gravitational effects would be distinctive and detectable. Some physicists think colliding cosmic strings might be sources of gravitational waves. Others think they might seed galaxy formation. Finding a cosmic string would be revolutionary, proving that the early universe went through phase transitions that left topological scars in spacetime itself. Then there are domain walls, two-dimensional defects where different regions of space settled into different vacuum states. And monopoles, point-like defects concentrating enormous energy into a singularity. Each of these would bend light and spacetime in characteristic ways. The fact that we haven't found these objects tells us something about the early universe. Either the phase transitions didn't happen the way we think, or they happened in ways that didn't produce stable defects, or the defects exist, but are so rare we haven't encountered one yet. But here's what's fascinating. These aren't just speculative ideas. They emerge naturally from well-established quantum field theory. Under the right conditions, these defects must form. The question isn't whether the physics allows them, but whether the universe's history created the conditions where they could form and survive. And if they do exist, they're spectacular demonstrations of gravity and quantum mechanics working together. A cosmic string is a quantum field defect held together by quantum mechanics, but its gravitational effects come from general relativity. It exists in both theories simultaneously, a bridge between quantum and gravitational physics. Everything we've discussed so far happens in our universe. But what if our universe isn't the only one? Cosmic inflation, the theory that the universe underwent a brief period of exponential expansion in its first fraction of a second, naturally predicts a multiverse. Here's how. Inflation is driven by a quantum field in a high-energy state. Eventually, this field decays to a lower energy state, ending inflation and releasing its energy as matter and radiation, the hot Big Bang. But quantum mechanics means this decay happens randomly, probabilistically. Some regions decay early, ending inflation there. Other regions continue inflating. The regions that stopped inflating become universes, expanding normally, cooling, forming galaxies and stars and planets. But the regions still inflating grow, exponentially larger, and within those regions, some spots decay and become new universes while the rest keeps inflating. This process never ends. Inflation is eternal. Our universe is one bubble in an eternally inflating multiverse, with infinitely many other bubble universes forming constantly, each potentially with different physical laws, different constants of nature, different properties. Some of these universes might have gravity stronger than ours. Stars would burn out quickly. Life would struggle to evolve. Some might have gravity weaker than ours. Stars might not form at all. Some might have light that travels at different speeds. Some might have different numbers of spatial dimensions. We can never see these other universes. They're beyond our cosmic horizon, separated from us by eternally inflating space. Light from another bubble universe can never reach us because the space between us is expanding faster than light. But their existence might be detectable indirectly. If another bubble universe collided with ours in the distant past, it would have left a distinctive pattern in the cosmic microwave background. We've looked for such patterns. So far, nothing conclusive, but the search continues. This raises profound questions. If most universes in the multiverse are sterile, unable to support complexity or life, and we find ourselves in one of the rare universes where physics allows complexity, should we be surprised? It's like being surprised that you're on a habitable planet when most planets are uninhabitable. You couldn't exist on the others, so of course you find yourself on one that works. This is the anthropic principle. We observe physical laws compatible with our existence because universes with other laws wouldn't have observers. It's controversial. Some physicists think it's profound. Others think it's a cop-out, replacing explanations with tautology. But here's what's undeniable. The laws of physics in our universe seem fine-tuned for complexity. If gravity were slightly stronger, the universe would have collapsed before stars formed. Slightly weaker, and matter would have dispersed too quickly for galaxies to form. The electromagnetic force, the strong nuclear force, the weak nuclear force, all seem to be balanced in a narrow range that allows atoms, chemistry, planets, and eventually life. Is this fine-tuning evidence for a multiverse where other combinations exist but don't produce observers? Is it evidence for design? Is it a coincidence? Or is there a deeper physical principle we don't yet understand that explains why these constants have the values they do? We don't know. But the interplay of gravity and light is central to this question. Gravity determines whether structures can form. Light determines whether information can propagate. Together, they define whether a universe can support complexity, computation, observation, consciousness. Now let's connect quantum mechanics to gravity in a way that might unify them. The relationship between quantum entanglement and wormholes. He was wrong. Entanglement is real. We verified it experimentally thousands of times. Entangled particles are connected in a way that transcends space. They're not separate objects that happen to be correlated. They're a single quantum system distributed across space. In 2013, physicists Juan Maldacena and Leonard Susskind proposed something radical. Maybe entanglement and wormholes are the same thing. They called it A equals EPR, connecting Einstein-Rosen bridges. Wormholes, with Einstein-Podolsky-Rosen pairs, entangled particles. The idea: when two particles are entangled, they're connected by a tiny quantum wormhole. The wormhole is too small for information or matter to pass through, but it exists as a geometric connection in spacetime. Entanglement isn't action at a distance through space. It's a connection through the internal structure of space. If this is true, it's revolutionary. It means quantum mechanics and gravity aren't separate theories. Quantum information and spacetime geometry are different descriptions of the same underlying reality. Entangle more particles, and you build up more wormhole connections, and eventually, you build spacetime itself. Some physicists are pursuing this idea seriously. Mark van Ramsdonk showed that in certain toy models, you can start with entangled quantum states and derive spacetime geometry from the entanglement structure. Space emerges from quantum information. This connects to the holographic principle we discussed earlier. If the universe is a hologram, with three-dimensional space emerging from two-dimensional information on a boundary, then that emergence might be mediated by entanglement. The quantum correlations on the boundary create the geometric connections that we perceive as space in the bulk. Light is central to this picture. Photons can be entangled. Shine a laser through certain crystals, and you can create entangled photon pairs. These photons might be connected by microscopic wormholes. When you measure one photon's polarization, you instantly know the others, not because information traveled between them, but because they're the same quantum system connected through the structure of spacetime. This is speculative cutting-edge physics, not yet experimentally confirmed, but it's based on solid mathematical foundations. Multiple independent approaches to quantum gravity string theory, loop quantum gravity, holography are converging on similar ideas. Spacetime is not fundamental. It emerges from quantum information and entanglement. If true, this resolves the black hole information paradox. Information that falls into a black hole doesn't disappear. It remains entangled with the Hawking radiation emitted by the black hole. The entanglement provides a quantum wormhole connecting the interior and exterior, allowing information to leak out gradually. Let's bring this home. Everything we've discussed isn't just abstract physics. It's the universe you live in. It affects you directly. Right now, photons emitted by the sun 8 minutes ago are hitting your skin. Having traveled through curved space-time, bent by the gravity of planets they passed, carrying energy that will be absorbed by your atoms and contribute to chemical reactions in your body. You exist because light and gravity created the conditions for life. Gravity collapsed clouds of hydrogen into stars. Those stars fused hydrogen into heavier elements: carbon, nitrogen, oxygen, iron, phosphorus, all the elements your body is made of. When those stars died, they exploded, scattering those elements into space. Gravity collected that enriched gas into new star systems. One of them formed the Sun and Earth. The atoms in your body were forged in stellar furnaces and delivered to this planet by processes governed by gravity. Light powers everything you are. Photosynthesis captures sunlight and stores it as chemical energy in plants. You eat plants or eat animals that ate plants, extracting that stored solar energy to power your metabolism. Your thoughts right now are possible because neurons are firing, using energy that ultimately came from sunlight, delivered to your brain through countless intermediate steps, all of which were possible because gravity created a stable orbit, keeping Earth at the right distance from the Sun. Every time you look up at the night sky, you're looking back in time. The light from stars you see was emitted years, decades, centuries ago. You're seeing the galaxy as it was in the past. You're a time traveler, receiving messages from across history, delivered by photons that have journeyed through warped spacetime to reach you. The same physics that governs black holes and gravitational lenses also governs GPS satellites guiding you to your destination. The same equations that describe the Big Bang and cosmic expansion also explain why clocks on airplanes tick faster than clocks on the ground. Physics isn't separate from daily life. It is daily life, understood deeply. Here's what should give you existential wonder. You are made of atoms forged in stars. Those atoms are arranged in patterns complex enough to be conscious, to think, to question, to understand. You are the universe examining itself. Every thought you have is quantum processes happening in neurons, governed by electromagnetic forces between atoms, held together by nuclear forces, kept on a stable planet by gravity, illuminated by photons from our star. You are not separate from the cosmos. You are a temporary pattern in its vast flow of energy and information, no less significant than galaxies or black holes, just organized at a different scale. The same forces that shape galaxies shaped you. The same light that reveals the early universe also allows you to read these words. And here's the profound realization. Because light takes time to travel, and because space is expanding, there are limits to what you can know about the universe. You exist within a cosmic horizon, able to influence and be influenced by only certain regions of spacetime. Your light cone defines your causal connection to reality. But within that horizon, you have agency. Your actions send information outward at the speed of light, affecting future events within an ever-expanding sphere. Every choice you make becomes part of the universe's causal structure, written into spacetime itself. You're not just observing the cosmic dance of gravity and light. You're participating in it. Now let's look forward to the deep future, to how gravity and light will shape the universe's ultimate fate. Dark energy is winning. The universe's expansion is accelerating. In a few trillion years, galaxies outside our local group will have receded beyond the cosmic horizon. Their light will be redshifted into undetectability. The universe will grow dark and empty. But even our local group won't last forever. The Milky Way and Andromeda are approaching each other and will merge in about 4 billion years, creating a giant elliptical galaxy astronomers call Milkomeda. The collision will be spectacular, but not dangerous. Stars are so far apart that actual collisions are rare, but the gravitational interaction will fling many stars into intergalactic space while settling others into new orbits. Our sun will die in about 5 billion years, swelling into a red giant, possibly engulfing Earth. Even if Earth survives, its oceans will boil away, its atmosphere will be stripped, and it will become a lifeless cinder orbiting a white dwarf, the small, dense, fading remnant of the sun. But the universe continues. In Waya years, 100 trillion years, the last conventional stars will burn out. The universe will enter the degenerate era, lit only by dim white dwarfs, brown dwarfs, and the occasional flash when dead stars collide. In YY years, even these dead remnants will have decayed. Protons might be stable forever, or they might decay with a half-life of perhaps 1,035 years. If protons decay, matter itself eventually vanishes. Planets, moons, asteroids, dead stars, all will gradually evaporate into radiation. By 10,100 years, only black holes remain. Everything that didn't fall into a black hole or escape a galaxy billions of years ago now orbits these final gravitational monsters. But even black holes evaporate via Hawking radiation. A solar mass black hole takes 1,067 years to evaporate. A supermassive black hole might last until 10,100 years or longer. And then, in the deep dark future, the universe becomes a diffuse sea of photons and elementary particles spread across ever-expanding space. Temperatures approach absolute zero. Entropy approaches maximum. Nothing changes. Nothing happens. The universe reaches heat death, not a dramatic end, but a gradual fading into cold, dark, featureless eternity. Unless we're wrong, unless dark energy changes, unless vacuum decay triggers a new phase transition, unless the holographic principle means the universe is a simulation that can be reset, unless quantum mechanics allows tunneling to new vacuum states where physics works differently. We don't know. We're extrapolating trillions of years into the future using physics we understand today. History suggests our understanding will change. Every century reveals new phenomena. A civilization in the year 1050 might look back at our predictions the way we look back at pre-relativity physics. Well-intentioned, but fundamentally limited by lack of knowledge. But here's what seems certain. Gravity and light will continue shaping whatever happens. They're woven into the structure of spacetime itself. As long as spacetime exists, as long as there's any energy to move through it, gravity will curve that spacetime and light will follow those curves. The cosmic dance continues, slower and colder, but never truly stopping until perhaps the heat death of the universe makes dance meaningless because nothing remains to move. With everything we've learned, let's be honest about what we don't know. Physics has revealed extraordinary truths, but enormous mysteries remain. What is dark matter? We've mapped it gravitationally. We know it's there, but we don't know what it's made of. Is it particles? Modified gravity? Something else entirely? Dozens of experiments are searching. So far, nothing. What is dark energy? We measure its effects. We see the universe accelerating, but we don't know why. Is it the quantum vacuum's energy? A new field permeating space? A sign that Einstein's equations need modification? The cosmological constant problem remains unsolved. What is quantum gravity? General relativity describes gravity as curved spacetime. Quantum mechanics describes everything else as quantized fields, but they don't fit together. At extreme conditions, the Big Bang, black hole singularities, the Planck scale, both theories are needed, but we can't merge them. String theory, loop quantum gravity, and other approaches are making progress, but we don't have a complete theory yet. Is information truly preserved in black holes? We think so, but the mechanism is unclear. How does information escape a black hole through Hawking radiation? The mathematics is subtle and incomplete. Is the universe infinite? We can see only our observable universe, defined by the cosmic horizon. Beyond that, we don't know. The universe might extend infinitely, or it might loop back on itself in higher dimensions. Current measurements suggest it's flat, which favors infinite, but we can't be certain. Are there other universes? Inflation naturally predicts a multiverse, but we might never observe it directly. Is the multiverse real physics or untestable metaphysics? Why these laws and constants? Why does gravity have the strength it has? Why does light travel at the speed it does? Are these values necessary, arbitrary, or selected from a multiverse ensemble? We don't know. What happened before the Big Bang? Maybe nothing time itself began at the Big Bang. Maybe our universe emerged from a previous collapsing universe. Maybe the question is meaningless because before requires time, and time didn't exist. This might be fundamentally unanswerable. What is time? We use it in every equation, but we don't deeply understand it. Why does time flow forward? Why do we remember the past, but not the future? Is time fundamental or emergent? The arrow of time is still mysterious. Why does anything exist at all? Why is there something rather than nothing? This might be the ultimate question, beyond even physics to answer. Maybe existence is necessary. Maybe it's contingent. Maybe the question contains false assumptions. These mysteries aren't embarrassments. They're opportunities. Every generation of physicists has pushed back the frontier of ignorance. Our generation will answer some of these questions, likely revealing new mysteries in the process. That's how science works. We've journeyed from the basics of gravity and light through black holes, gravitational waves, quantum mechanics, and the ultimate fate of everything. Now let me give you the final revelation, the one that ties everything together. The universe began 13.8 billion years ago in a hot, dense state. For hundreds of thousands of years, it was opaque to light. Then it became transparent, and light streamed freely through space. That light, redshifted to microwaves, is still traveling, carrying information about the early universe. Gravity pulled matter together, forming stars. Those stars created heavy elements and scattered them through space. New stars formed, with planets. On at least one planet, around one ordinary star, chemistry became complex enough to be self-replicating. Evolution began. Over billions of years, simple organisms became complex, developed nervous systems, developed brains, developed consciousness. And now, 13.8 billion years after the beginning, parts of the universe have become aware of themselves. You are one of those parts. You are made of atoms forged in stars, arranged in patterns complex enough to wonder about their own origins. When you look at the night sky and see stars, you're not separate from what you're seeing. You're made of the same elements, governed by the same forces, woven into the same spacetime. The light entering your eyes connects you causally to distant stars. You're receiving information that traveled for years or centuries or millennia to reach you. Information encoded in electromagnetic waves that followed geodesics through curved spacetime to arrive at your retina at this exact moment. And your brain, processing that information, is engaging in one of the universe's most remarkable activities, understanding itself. The universe, through you, is examining its own structure, history, and fate. Every scientific discovery is the universe learning about itself through conscious observers it has created. This isn't mysticism. It's physics. You are quantum fields in particular arrangements, held together by electromagnetic forces, kept on a planet by gravity, powered by energy from nuclear fusion in a star 93 million miles away. Thinking thoughts enabled by quantum processes in neurons, understanding concepts like space-time and event horizons and gravitational waves. Gravity and light don't just shape the universe. They shaped you. Every force we've discussed, every phenomenon we've explored, contributed to your existence. You wouldn't be here without nuclear forces creating elements in stars, without gravity collecting those elements into planets, without light from the sun, powering the biosphere that created and sustains you. And here's the empowering part. Your actions matter. Every decision you make sends information into the universe at the speed of light. Your influence propagates outward through your future light cone, affecting events, changing probabilities, becoming part of the causal structure of space-time itself. You're not a passive observer of the cosmic dance. You're a participant, a temporary but significant pattern in the universe's vast flow of matter and energy and information. Billions of years from now, long after humanity is gone, the consequences of your choices will still be written into the universe's history. Every photon you reflected, every gravitational wave you infinitesimally contributed to, every causal chain your decisions initiated, all of it becomes part of the permanent structure of spacetime. You cannot be erased from cosmic history. Your existence, however brief on cosmic timescales, is an eternal fact about the universe. Think about that. Every kind word you've spoken sent sound waves through air that eventually dissipated as heat, increasing the universe's entropy in a specific pattern. Every step you've taken has gravitationally affected every object in the universe by infinitesimal amounts. Every photon that's bounced off your body has carried information about you, outward at the speed of light. And that information is now light years away, still traveling. A permanent signature of your existence spreading through space. You are not insignificant. The idea that humans are tiny and meaningless in a vast cosmos misses the point entirely. Yes, you're small compared to galaxies. But galaxies don't think. Galaxies don't understand. Galaxies don't create art, music, mathematics, or science. You do. Consciousness and understanding are the rarest and most complex phenomena we've discovered anywhere in the universe. A galaxy contains hundreds of billions of stars, but as far as we know, none of them are aware they exist. You are. That makes you more remarkable than any galaxy. You're not just matter arranged in space. You're matter arranged in such a way that it can contemplate its own existence, understand its origins, and wonder about its place in the cosmos. The same physics that governs neutron stars and gravitational lenses also governs your brain. The same light that reveals distant galaxies also allows you to see the face of someone you love. The same gravity that shapes cosmic structures also keeps your feet on the ground. You're made of the universe, and you're using the universe's laws to understand the universe. That's not small. That's miraculous. And here's what should fill you with both humility and awe. Right now, at this very moment, you're standing on a planet orbiting a star in a galaxy containing hundreds of billions of other stars, in a universe containing hundreds of billions of other galaxies, most of which contain billions or trillions of stars of their own. The scale is incomprehensible. The numbers break our intuition. But that same vast universe, through chains of causality stretching back 13.8 billion years, through the formation of elements in stars and the assembly of planets and the evolution of life and the development of brains, has created you. A being capable of understanding relativity, of grasping quantum mechanics, of comprehending that light and gravity shape everything. You understand things that Isaac Newton didn't understand. You know facts about the universe that every human who lived before 1900 couldn't have known. You've learned in a few hours what took humanity thousands of years and millions of scientists to discover. That knowledge is now part of you, physically encoded in the neural connections in your brain, in patterns of synapses and neurotransmitters that exist right now in three-dimensional space inside your skull. When you look at the night sky now, you'll never see it the same way. Those points of light aren't just pretty. They're messages from the past, photons that have traveled through warped space-time, carrying information encoded billions of years ago, arriving at your eye at exactly this moment in cosmic history. You're receiving ancient light, bent by gravity, redshifted by expansion, delivering news about what the universe was like when those photons began their journey. And you understand this. You can think about a photon's journey through spacetime. You can visualize curved space. You can grasp that black holes bend time. You can comprehend that the universe is expanding and will eventually grow cold and dark. These aren't just facts you've memorized. They're part of how you understand reality now. Your worldview has been upgraded with concepts that most humans throughout history never encountered. So here's my challenge to you. Don't let this knowledge sit passively in your mind. Use it. Let it change how you see the world. When you use GPS navigation, remember that it works because engineers accounted for relativity. When you look at stars, remember you're looking back in time. When you feel small under a vast sky, remember that your ability to understand that vastness makes you cosmically significant. Share what you've learned. Explain to someone how gravity bends light. Tell them about gravitational waves revealing colliding black holes. Describe how the universe is expanding and what that means for the future. Every time you share this knowledge, you're fulfilling your role as part of the universe's self-awareness, helping other parts of the universe understand themselves. Stay curious. Everything I've told you today is our current best understanding, but science continues. New discoveries are being made constantly. Gravitational wave astronomy is still in its infancy. Quantum gravity theories are being developed. Experiments are searching for dark matter. Telescopes are probing deeper into space and time than ever before. Maybe someone watching this video right now will make the next breakthrough. Maybe you'll be the one who discovers what dark matter is, or solves the information paradox, or unifies quantum mechanics and gravity, or proves the multiverse exists. The universe revealed its secrets to people throughout history: Galileo, Newton, Einstein, Hawking, and it will reveal more secrets to people in the future. Why not you? Before you leave, do me one final favor. Look up at the sky tonight, whether it's day or night where you are right now. If it's day, look at the sun, not directly. Don't hurt your eyes, but acknowledge that you're seeing photons that left its surface 8 minutes ago after being created by nuclear fusion in its core. If it's night, find the brightest star you can see. That light has traveled for years to reach you. You're seeing that star as it was in the past, and gravity has bent that light's path ever so slightly on its journey to you. And realize, you are the universe looking at itself. Through your eyes, the cosmos contemplates its own existence. Through your mind, space-time becomes aware of its own curvature. Through your wonder, reality appreciates its own magnificence. That's not just poetry, that's physics. That's the literal truth about what you are and where you fit in the grand cosmic dance of gravity and light. If this journey has changed how you see the universe, hit that like button. Subscribe for more deep dives into how reality actually works. And drop a comment telling me, what was the moment that blew your mind the most? Was it gravitational lensing revealing dark matter? Black holes bending time? The holographic principle suggesting space is emergent? Virtual particles in the quantum vacuum? Or something else entirely? And remember, every time you look up at the night sky, you're not just seeing stars. You're seeing history. You're witnessing the cosmic dance of gravity and light that's been shaping the universe for 13.8 billion years. You're participating in the universe's journey of self-discovery. Welcome to cosmic consciousness. You're part of something magnificent, and now you understand why. Thank you for taking this journey with me. Keep looking up, keep questioning, and never stop wondering. The universe is far stranger and more beautiful than we ever imagined, and we've only begun to understand it. Until next time, remember, you're made of stardust. You're thinking with quantum mechanics, and you're standing on a planet held by gravity while light reveals the cosmos to you. That's not just your reality. That's your glory.